Okay, so here is part 2 of my exam review. We're picking up with number 6. So consider the reaction between nitrogen dioxide and carbon monoxide. There's some slight formatting errors, but NO2 plus carbon monoxide to form nitric oxide and carbon dioxide. The rate constant at 701 degrees Kelvin is measured at 2.57, I guess 1 over meters per second, essentially. And at 895 degrees Kelvin is measured at 567 meters. So find the activation energy for the reaction in kilojoules per mole. So given that it's given a rate constant and it's giving me 2 comparative values, I'm going to want to use the 2-point Arrhenius equation, which is ln K2 over K1 equals EA over R times 1 over T1 minus 1 over T2. So it's important to note that this is not negative right here. Like, that's not negative, and that, with the Clausius-Clapeyron, it was K2 over K1, and then it was T2 minus T1. But for this one, it's K2 over K1, and then T1 minus T2. So don't let that confuse you. But what I essentially am going to do, and going to assign T1s, T2s, and K2s. So I'm going to make this first line of data my K1s, and this is going to be my K2s. So now it's just plugging in. So I have ln of my K2s on top, so 567 over 2.57 equals, and it wants to know about the activation energy over R, and the R you use here is going to be that 8.314, because it's dealing with energy. And then for my temperatures, it's going to be 1 over T1, which is 701, minus 1 over 895. So when you do it the right side, you should get something like 3.092 times 10 to the negative 4. And then on the left side, you should get 5.396, and so that's going to be EA over 8.314. So when you multiply everything over and simplify, you should get an activation energy of 145.084 kilojoules per mole. So I converted this from joules to kilojoules. So if you get something like 145,000, that's you're still correct. All right. Moving on, would you expect a reaction that is unimolecular or bimolecular to proceed faster? So by unimolecular and bimolecular, meaning, let's say something that's unimolecular would be like a decay. So let's consider like the decay of water. I don't know. So like H2O to form like H positive plus O negative, which that's just the autoionization of water, which you'll get into in chapter 16, or I guess chapter 17. But so that would be unimolecular as in like one reactant versus something that's bimolecular, which would be, sort of the reverse, OH plus H, or hydroxide plus hydronium ions to form, or I guess hydrogen ions, I'm so sorry, to form water. So something that is unimolecular only has to depend on the concentration basically itself, versus, let's say, something that's bimolecular, you need to worry about 2 different components. So I would expect something that is unimolecular to proceed faster solely because I don't have to make sure 2 different substances are oriented properly, have enough energy to react. I'm only worrying about one thing. So pretty common sense, you would think something unimolecular would react faster. So the rate determining step is just simply going to be your slowest step, right? So think of like, let's say you're in a relay with some of your classmates. The slowest person on your team is going to determine what place you're going to be overall. Everybody else can be fast and beating everyone else, but if you have someone who's really slow, then they're going to hold everyone else back, and so that's going to be your rate determining step. Let's see. With these type of questions, I see more conceptual questions being asked on them, so that's why I sort of included them there. What 2 factors must be satisfied for the elementary step / mechanism to be validated? So essentially, I'll just write it up here. I need the sum of the steps to add up to the overall. And what I mean by this, let's say well, I'll get to it in 10, right? But these two steps right here essentially need to add up to form this step right there, right? And so you do that by just adding straight down. If they're on the opposite side of the arrows, it means they cancel out, right? So like, for example, oxygen here and oxygen there will cancel out. All right, and so then I'll get to that though. And the second step is that the rate law will match the proposed rate law. Or essentially you can manipulate like these rate laws for each of these to match the overall. So, with that being said, we can move on to 10. So 10 tells us that ozone naturally decomposes to oxygen by this reaction, 2O3 to form 3O2. The experimentally observed rate law for the reaction rate equals KO3 squared times O2 to the -1. Show that this proposed mechanism is consistent with the experimentally observed rate law. So what we have to do first is make sure that they sum up. And we sort of already did that. So we canceled out what on opposite side of the arrows. And so when you just add this straight down after that, you get 2O3 to form 1,2. Oh, there's a 2 right there. 3O2. So yeah, so we already know right there that mechanism adds up to the overall. Don't forget that little 2 that's right there. Sorry, it's not on the same line. So then what you want to do is just write out the rate laws that you can have, right? So these double arrows tell me that it's reversible, meaning I can have a K1, which is my forward reaction, and a K-1, which is my reverse reaction, right? And we know that K1 and K-1 are going to be equal at, the rates will be equal at equilibrium. So I can set these rates equal to each other to sort of manipulate these equations, right? Because if I just took these rate laws as is, it's going to have this intermediate right here, which is oxygen. So I have to essentially manipulate these to get rid of that unimolecular oxygen to essentially match that. And because this is my slow step, what I'm going to do is essentially find the rate law of the fast step, and then I'm going to plug in to the rate law of the slow step. Because remember, our slow step is our rate determining step. So my rate is like whatever I get from up here is going to plug in overall into that bottom one. So sorry about my crazy arrows. Now let's get into the actual problem. So I can write a K1, I can write a K-1, and then because I have the slow step, I can write a K2 and a K-2, but you may not need them, but we'll see. All right, so my K1, or I guess for the first part, so it'll be rate equals K1 times O3, okay? My K-1 is going to be rate equals K-1 times O2 times O. Right? Okay, and then my K2 is going to be rate equals K2 times O3 times O, and then my reverse for that K-2, so rate equals K-2 times just O2 squared. All right, so what do I want to essentially do is I want to get rid of this intermediate. This cannot be in the overall rate law, and that's why you can't just say, oh, this is my rate law, O3 times O, because an intermediate cannot be in the overall rate law, right? So what I want to do is I'm going to take these first two right here, because I see it has oxygen, and I see it has a forward and reverse reaction. So I want to essentially isolate the concentration of oxygen, and then I can plug in for what it equals. So what I mean by that is I can set these rates equal, because at equilibrium, the forward and reverse reactions are the same, or the rates of them are. So K1 equals K-1 times O2 times O. So what I want to do now is essentially I just divide both sides by K-1 times O2. So I'm left with K1 divided by K-1 equals O3 over O2 equals O. So what I can do now is I can now plug in to that K2, right? It turns out that you didn't need this K-2 right here because it's not really helpful. What I can do is I sub in to that K2, which is my rate determining step. And so what I'll do is I'll put rate equals K2O3, and then whatever I had from right up here. So I'm going to put K1, K negative 1, O3 over O2. So when you clean this up a bit, you can sort of disregard the K2s and the K1s and just synthesize that to be K. Just kind of ignore that. And then you'll have O3. So we know when we have 2 of something, you know, they're exponents. So multiply something by itself, that's going to be O3 squared. And then this on the bottom right here is the same as O2 to the negative 1, right? So O2 to the negative 1. So if I look, I go up here, I go boop, 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 boop. That matches. So I know that that is valid, and that's how you do the problem, right? Okay, keep practicing those in the book. I think they can be confusing if you don't practice with them. So I highly recommend that. That's definitely a problem to pay attention to. So describe what an intermediate and a catalyst are. How exactly does a catalyst affect the reaction? So the way I like to sort of go about it is an intermediate is something that is formed by one reaction and used up by another. So it's a product of one and then used up immediately after. So the difference between, so for example, if I go back to this number 10, I see this right here. It appears as a product in this first equation. And then in the next step, it's used up as a reactant. So that's an intermediate, okay? So the difference between that and a catalyst is that a catalyst appears as a reactant, and then it also appears as a product, meaning it's never used up. An intermediate is used up. So not used up. And then used. So intermediate, it's usually immediately used up. It's usually a high energy molecule, etc., but that's not really important. So intermediate is used up, catalyst is not. And what a catalyst does is essentially increases the reaction rate by decreasing the activation energy. Remember we talked last time about how a higher activation energy is going to make a slower reaction. Well, a catalyst will lower that activation energy, okay? All right. So what we do now is, let me just clean this up because I don't know why you converted them all to A's, which is whatever, I guess. All right, so the mechanism shown is proposed for the gas phase reaction to N2O5 to form 4NO2 plus O2. What rate law does the root mechanism predict? Okay, so essentially what I like to do first is cross out what is eliminated, right, on each side of the reaction. So if I look, I see that there's an NO2 that's eliminated, and there's an NO2 eliminated here. These two right here still stay. Okay, so now let's see what else can be eliminated. This NO3 can also be eliminated. Okay, and let's see anything else that can be eliminated. NO or the nitrous oxide or nitric oxide can also be eliminated. All right, so now what I do now is I just sum up to all my other steps. So I'll start writing that over here. So I get 2N2O5 to form 4NO2 plus O2. Okay, cool. So just like last time, you essentially want to, whatever you have, plug in down here. So I can have a K1 and a K negative 1 right here. I can have K1, K negative 1. And for the second part, I can have a K2. There's no reversed arrow, so I know it only has the forward reaction, and then I can have a K3. It's for the same reason. I don't have a reverse reaction. If there's a reverse reaction, you're going to see the double-headed arrows, or it's going to look like that, right? So these two right here have no reverse reaction. So same thing as before. I just kind of like to write out my possible rate laws. So I have rate K. So rates, I'm just going to write that out. K1, K negative 1, K2, and K3. All right, so what I'm going to do, so K1, the forward is just going to be, well, I guess I don't want to put equal signs. It's just going to be N2O5